Good morning, everyone. How many? Five of you are here. You all right? Well, just a quick reminder that we got a message from the academic head last night. I got an email. So that literally says that from today, of course, we are doing it, but from today, strictly, the attendance must be taken within the class hours. So what it means is sometimes I get some emails after the class. The teacher, I was there, I just left, I just went to toilet and you took, there's no way to verify uh, what you were doing, whether you were there or not, literally. Right. So this time, from today, I can't do anything about it because I most likely, they're going to disable the link that they used to give the teachers to update your attendance within 48 hours. You know what I mean? But we can't update it within 48 hours. I have to take it just during our session slot. And we have been doing it. But that's not the issue. The issue is here that I do get requests from students saying that after the class hour, sometimes we email the teacher, I was there, I couldn't do it. So don't do it. Right. So I'm more careful when I take attendance, just in case any of you missed it, for whatever reason your mic was broken or whatever. If you are still, we are still in the session, you, within the session time, send me a message. You don't have to interrupt me, send me a message. So basically, my rule is to take the attendance as usual, and then go and check if someone has sent me any message. Okay, on the text box. If I see that someone has said, teacher, I'm here, but my mic was broken, all right, I will take the attendance. But I can't do, as I say, they can't really do anything anymore after your 90 minutes have expired. Okay? I'm not going to do anything. If you have to do anything, you have to go straight to the director of the campus or the academic department, and there's a whole lot of hassles involved in it. So that's not my responsibility. So be careful about that. And I will take the attendance from now on. Let me see. They must have removed that link. Let me take a quick look. I think they haven't removed it yet. I can still edit, but that's the email that we received. It is for your knowledge that we can't update it. The things will be updated pretty soon. That's for sure. As you can see right here on your screen, I think the Vietnamese version you can understand. Starting tomorrow, you are requested to take students' attendance during each slot's class time. It's not within 48 hours after score as for now. For any reason, you can take attendance during the student slot time. Please send an email to the Department of Academic Affairs. It will present it to the campus director for consideration. So there are issues there. All right, it's just for your quick reference. So these are things are going on. So you need to be aware of these things. Now tell me, where were we? I remember we were talking about this IO, and I told you that I'm going to give you, let's say, some case, right? So are you ready to deal with the algorithms straight away, early in the morning? It's good, actually. So in last class, we talked about the algorithms, correct? So we are supposed to move into the IO part, into these few things that we have right here. But do you have any question about the algorithms? Let me talk about it first. That we talked about disk arm scheduling algorithms. Okay. If you have any question, ask me. Any of you have any question at this part? And we covered it in the last lecture, right? On Monday. Disk arm scheduling algorithms. Yes and no. I think we did. So, any of you, are you interested in giving some answers? So I can give you a case. Okay, I will give you the case later. Just the beginning of the class. I know many of you, you are just getting warmed up for the lecture. And later, right in the middle, I will give you the class. So let's get to the beginning and see some of the interesting things that they have talked about right here. In the IO chapter, we have already left the file system behind and moved into IO chapter. And as we move into the IO chapter, the first thing that we have decided to discuss is disks, because that kind of like bridges the gap between file system and IO. It is an IO device, whereas it needs the file system to map it. That's why we are here. A few things that we'll be touching on is this. The disk hardware. Talking about disk hardware, you already know the things, the components that we have. We have a spindle, and we have the arms. We have the platter. In fact, platters, stacker platters. Assembler, controller, and then we have the read and write head. So these are the hardware, the actual hardware that you have inside. And but I strongly recommend that you go to my YouTube channel and just take a look at this short video I've shared, or just search in Google and find some videos where they're actually showing it, they're cracking open their hard disk, that what hardware is inside. Okay. That is what we have. But this is the hardware part. This is the hardware part. But this hardware is interpreted in terms of a few logical things by the controller, and that is cylinder, sector, and track. So these are all logical things. So naturally, when you pass a command, you communicate with file system. It needs to be communicated. You want to give an instruction to the controller to write something on somewhere on the disk, then it must contain the cylinder number and sector number. And in the last class, before we left, in our algorithms, the bunch of algorithms that we discussed, okay, elevator algorithms, light modification of elevator algorithms, then shortest seek fast, and first come, first serve. These algorithms, we are essentially talking about how to reduce the seek time. So I would think this one. This one we already studied. Okay. So let's see what else we have right in there. So we understand the hardware. Now, RAID level. The first thing that we're talking about is RAID level. That is important. What does it stand for? RAID stands for Redundant Array of Independent Disks. It's a data storage virtualization. Again, you can see the virtualization technology, which literally means, again, a logical thing. Okay. So we imagine that there are stacks of disks, we call drive. But by the way, as we use the word, we'll be using the word drive. A stack of disks, that means a drive. But this drive has nothing to do. This drive is not your C drive or D drive. Okay? Don't confuse this word drive with a C drive or D drive. It is a virtualization, which basically means it is a part of imagination that the way we structure the data, the way we store the data, and there are definitely reasons for that. And the reasons are purpose of data redundancy and performance improvement, or both. So some of the RAID levels are taking care of data redundancy, some of them are performance improvement, and some of them are taking care of both of them. And this is really, really important, right? So talking about RAID levels, we split it out. Well, please don't forget these words: redundant array of independent disks. Sometimes we also call it redundant array of inexpensive disks. Both of them, inexpensive or independent. Both are okay. So please remember the expression, the word. Talking about the RAID levels, we have two different clusters of RAID levels. Two different clusters. In one cluster, we have RAID level 1, we start with RAID level 0, then RAID level 1, RAID level 5, RAID level 6, and RAID level 10. This is one cluster, and we will see why we put them in one cluster. In another cluster, as you expect, that we have RAID level 2, RAID level 3, and RAID level 4. That is another cluster. So we have two different clusters of RAID levels. Okay. And they do the same things, of course, but they do it in slightly different way. And that's what we are going to understand. The first, some of the important things. We do it to ensure parallel processing. So it is a virtualization, like a storage virtualization. That is what we call it. To speed up the CPU performance through parallel processing, side by side. The redundant array of inexpensive gives a redundant array of independent bits. 6 schemes 0 to 5. In fact, now we have 1, 0, 10 as well. Straight away, they have jumped into 1 zeros. Now, I will take a get out from here and would like to show you another one where things are better organized than our slides. Let's first take a look at rate level, the first cluster of rate levels, as you can see right here. Okay, if you are interested. I can share the link with you, so on your own you too can check it out. If you want, check it out right there. So what is the rate level? The rate level, as we can see, in these clusters, because as I said, there are two different clusters of rate levels, okay? The reason we mentioned there are two different clusters of rate levels is essentially they do the same things. Okay, purpose is performance enhancement and backup. And they do the two things, but in a slightly different way. Technically, they do it in a different way, and we'll talk about it. So let's first get introduced to all these, the members of each of these clusters. So in the first cluster, we have rate 1, rate 0, rate 1, rate 5, rate 6, and rate 10. You need to remember these words. Rate 0 is striping. Literally, that means that you stripe it down into two parts. In other words, when it comes to writing the file, okay, you don't put everything of the file in one place, in one drive. You split it into two parts. What do we gain by doing it in that way? Doing it in that way, we gain in speed. And that's what we mentioned just now. If you can still remember, we talked about parallel. Where was that? Parallel processing. That's exactly what we do. For parallel processing, that means right now you can engage two heads, two read and write heads, to do the data transfer at the same point of time. So naturally, you double the speed of data transfer, because now instead of just one head getting engaged, one read and write getting engaged, read and write head or one arm getting engaged, you are engaging two arms and two read and write heads. Okay, that is the concept. Also, from backup point of view, doesn't really serve any purpose, but it's obvious that we don't expect that the two drives will fail together. These are called the drives, as you can see, drive 1 and drive 2. Okay, this drive, again, this is the drive that you shouldn't confuse with your C drive or D drive. That's totally different. It doesn't help in backup. It only helps in speed. You can double the speed of data transfer, both reading and writing. And this is called striping, so a word that you must remember. Rate level 1 is called mirroring. Mirror. Okay. The morning after shower, you look at a mirror, look at your reflection in the mirror. Okay, when you are dressing up. So that is mirror. So what does it mean? The name suggests that you make a backup. So rate number 1, rate level 1, takes care of backup, not striping, not speed. Rate level 0 only for speed. Rate level 1 only for backup. So basically, whatever you write in one drive, you make a copy of that in drive 2. So at any case, in any point of time, we don't expect both the drives to go bad. I mean, develop bad sectors or get corrupted. So naturally, if one of these drives gets corrupted, the other drive will survive. Then we have RAID level 5, which is basically striping with parity. But first I will move on to talk about RAID level 1 plus 0, which we call 10. RAID level 10 or 1 plus 0, basically it combines both mirroring and striping together. Because as you can see right now, they have been mirrored because block 1 mirrored in drive 1 and drive 2. These are mirrored drives. So it serves the purpose of backup. And also it has been stripped down into two different parts. So the first one is the first set, block 1, and block 2 is right here in drive 3 and drive 4. That is really good, but as you can guess, that if you want to store your data in that way, you need a huge amount of space, isn't it? Like, for example, if you have 100 GB of hard disk space, so literally, in effect, you can only use 50 GB to store fresh new data. Because the other 50 GB here will be a kind of backup for this one. So that's why we introduced a couple of new concepts. That's called striping with parity. Striping with parity. A very important issue. Striping with parity and striping with double parity. Like a further backup. Now, what is a parity bit? A parity bit, parity drive, the word parity literally means it is a kind of checksum. Well, you don't know checksum yet. We will find the checksum. It's an algorithm. It is an algorithm. It's not the exact data, but this algorithm will help you to reconstruct or rebuild everything that was in a particular drive. So what we do in striping is naturally the parity block that we call the parity block was the algorithm that you can use to rebuild any of the lost blocks. Okay, so the parity block is an important concept, and also the more important because it doesn't consume the backup, that much of backup. So as you can see, we have done striping, three-level striping, basically. Drive 1, drive 2, and drive 3, all right? So this is 1A, 1B, and 1C. So the file 1 has been stripped down into 3 different drives, right? Good, more speed. And the 4th drive, we store a parity bit, a parity block. This parity block will help you to rebuild any of these blocks in case there is a drive failure. So it serves the purpose of backup. And the technique is we don't store the parity drives, the parity blocks of each of these files, like file 1, file 2, file 3, file 4. For each of them, we don't store the parity blocks in one single drive, because that drive fails, everything will be gone. We kind of like distribute it that way. And just looking at this picture, you can see now, even if one drive fails, you can always recover. Well, say for example, this drive fails, the second drive. That means drive 2 fails. So what do you lose? You lose block 1B. Don't worry, you have the parity for block 1. You can easily rebuild it. You lose block 2B. Don't worry, you have the parity for the block 2, and you can easily rebuild it. And how about this one? In this case, only the parity block is gone, so no worries. The original blocks are still there, and it's the same. The 4th is the same. We have the parity, so you can use the parity block to rebuild the lost block, the data of the lost block. That is the technique that we use. We also have level 6, which is called double parity. Obvious, you understand. A double parity gives you an extra guarantee that now if two drives, which is extremely rare, but just in case two drives simultaneously fail or crash, still you can recover everything. Two drives. In the case of with single parity, one drive failure, any one drive failure. But in the case of 6, starting with double parity, you can now recover everything. Okay. If there are two drives that fail together. All right, so this is the first cluster that we have. However, what they do, that's where the difference comes from. What they actually do is again, we'll get back to these workspace soon, so I activate this. The one thing, the difference that I was talking about, because we just mentioned the clusters, right? So what were the two clusters that we were talking about? So in the one cluster, in the first one, we had, in the first cluster, what did we have? We had, I switch on my camera because it's getting too hot. Switch off my camera. In the first cluster, we have the RAID level 0, 1, 1 and 0, 5 and 6. This was the one cluster. Another RAID cluster had 2, 3, and 4. They do two things. One is striping, and another one is mirroring. Or both of them together is plus n, or even better, striping plus parity. Because parity will give you the recovery strategy. It's not exactly a backup, but it is a recovery strategy for recovery. We saw that now even two drives fail together, you can still recover the lost data. But in the case of, so how do they do it? In this cluster, they do it by maintaining parity block. Because remember, we are talking about block. Everything in the first cluster is measured in block, or done in block, or compared in block. Block is the unit. Okay. The same things are done right here in the second cluster, but this is at the bit level. That is the main difference. We do striping, we do maintaining, we do maintain parity bit, not parity block. And that is what we call the RAID level. So first, let's look at it. And for that, we'll be introduced to a new word. You'll see it right here, and you'll be seeing it right over there as well. Okay, just in case you want to check it out. I also share this link. If you want, you can read it and check it on your own. So what do we have? Here, the RAID level 234 and how it works. The bit level striping, this is the first word that catches your attention. Bit level striping with dedicated Hamming code parity. Hamming code parity. Now, Hamming code is a code. You don't have to go too deep inside Hamming code. Of course, if you want to know more, you can go and learn about it. Hamming code literally, but you have to remember the word Hamming code. So Hamming code literally means it measured the distance. For example, when this particular code has been copied right here, how do you ensure that it has been copied in the proper way? The way to do it is to introduce an extra bit right here, or anywhere, and it depends on some logic and algorithm. An extra bit, that is called the Hamming bit. So if this is the Hamming bit, when it has been copied, you will measure, you will compare the distance of each bit from these newly introduced Hamming bit. So by ensuring that the distances are okay, and that is one of the ways to measure that it has been properly copied or not. So there isn't any data loss. So that is what we call the Hamming code parity. In the case of the RAID 2, all the data is striped. It is striped, okay? To the bit levels, not blocks. Each bit is written on a different drive. You can see different drive or stripe. Now, such a solution requires the use of Hamming code for error correction. When you do a bit level transfer, then you need the Hamming code for error correction. Hamming code is a linear error correcting code named after inventor Richard Hamming. Hamming codes can detect up to d-1 bit errors. Okay, bit level errors and correct d-1 by 2 bit errors, where d is the minimum Hamming distance between all pairs in the code words. So thus reliable communication is possible when the Hamming distance between the transmitted and received bit patterns is less than or equal to d. Okay. By contrast, the simple parity code can't correct errors and detects only an odd number of errors. So these are much better in terms of backup or parity. Rather than going for the parity blocks, we go for the Hamming code parity. Okay, and that is exactly what we do. So what is spatial RAID 2? It's striping. The same thing with RAID 3, another rare one. RAID 3 works as RAID 0 does. So that means striping. Although it explicitly uses byte level striping, it also uses an additional disk in the array. It is used to store checksums. Remember, I just mentioned the checksum. So checksum is an algorithm that will help you to build the entire block. And it supports a special processor in parity codes calculating, so we may call it the parity disk. It's a totally separate disk that it uses. It's a very rare. Finally, 4 works similarly to RAID level 3 and 5. Okay, 4 is very similar to RAID level 3, and the main difference is a way of sharing data. The way you are sharing the data. They are divided into blocks 16, 13, 64 bits, 64 KB, and 128 KB, and written on this. These are actually the rare ones, the ones that you need to focus on. And as you can see right over there, going back to our the things that we had over here. We'll quickly go through to see what are the ones we are talking about. They talked about rate level 0. Indeed, you have to understand the rate level 0, of course. Why you can't write? Okay. So we have rate level 0. That is something that we need to be careful about. And that is important, which is basically striping. Okay. Then you can also check out that advantage and disadvantage. Rate level 1, metering. Did they use the word? No. But remember, is metering. Then rate level 2, it is striping with Hamming code. Striping at bit level, not block level, with Hamming code. Rate level 3, the rare one, it stores the parity in a separate disk, not with them. Bit level, but for all of them, they store a parity, an extra level of caution. And then read level 4 and 5. So basically the 5 is the most important one, where you introduce the concept of single parity striping with parity. Strips, striping, plus parity blocks. So these are the ones that you will have to remember. It's clear? The rate level. Just give it a read and try to remember what was what. We already covered this part. We are not going to spend too much time, but we'll just sail through. So you can see them, and if you have any question, you can ask me. If you want, I leave it up to you. If you want, I can give you a case, and we can work on this together. But for that, we need your engagement. If you are not engaged, then in the end, I give you the question and I give you the answer. Well, that's better not to do it. This ARM scheduling algorithm is very important, as I say. First come, first served. Basically, when we do the calculation of average seek length, the purpose of doing this is to reduce the average seek time. And that is definitely dependent on the average seek length as well. So we have 640 divided by 8, which is 80, is quite a lot. But then we move on to shortest seek fast. And shortest seek fast, as we can see, we compare each of them. It does take a little bit of time to find out which one will be the shortest displacement. But the point is, the problem, as we mentioned, it is not a fixed number of cylinder requests. New cylinder requests are getting added constantly at the end. And so naturally, to accommodate them, we need to be careful, because what will happen if new ones come, and then there will be a tendency that the cylinders will get better served rather than the cylinders on the flanks. So that will create a problem. 29.5. That's an average one. Okay, but it is a huge improvement. But there are always some problem.
Oh, what do you say?
So that is exactly what shortest seek fast was all about. But the most important ones are yet to come up, and that is the disks. Okay. What are the disks? The disks that we have an elevator algorithm. Elevator algorithm, as we know, that elevator is going to have an upward movement or a downward movement. So it either it is moving down or it is moving up. Moving up or moving down. So naturally, if it is moving up or it is moving down, depending on that, we will have two different algorithms. And that's exactly what we are looking at. If it is moving up, the pattern will be different. If it is moving down, the pattern, there will be another pattern, of course. Okay. When a request finishes the disk, the elevator drive checks the bit, then we keep track of this movement pattern, the upward movement or the downward movement, and we keep track of it by using the bit that we assign to it. There are two different algorithms, and the calculations are different. As you can see, the first one gives us a little bit of an improvement, 26, but the next one is 37.375. That means when you're moving up, you don't really gain anything from that. So we modified a little bit. We said slight modification of elevator algorithm. That's the most important one. And this one has two assumptions to start with. The first assumption is that the elevator never goes downward. It always keeps moving upward in one direction. Okay, it's always moving upward in one direction. It's moving up and up and up. So basically, when it reaches the 183, the highest number, then it will move to the lowest one, 14, because from there it will start moving upward. This is the first assumption. So the assumption is the first one is that it is always moving up in the upward direction, and the second one is, in effect, the lowest number cylinder is thought of as being just above the highest number cylinder. So basically the displacement, now if you go there, you can see that this is the arrangement. It went to the topmost one, and then from there, basically it went to the bottommost one. But this distance is assumed to be zero. Well, we can do these assumptions, not difficult, because by doing this little bit of assumptions, we can actually relate it. Okay, it's possible because cylinder itself is a concept. So that is what it is. So we have the total head movement, and as you can see, that particular calculation, 183 minus 14, is 0 on the chart. It is missing right here. Okay? So what we get is 19.125. That is something that we get. That's a huge improvement, of course. So, in general, that is what we studied, right? The next one that we get is a few other discussions about the disk scheduling algorithm. We are basically talking about certain scenarios. The scenarios that we are discussing right here, the first one is the controller provides a way for the software to inspect the number first. The current sector number under the head. And the reason to do it is because there could be 2 or more requests for the same cylinder. If that happens, then they can be done together. If 2 or more requests for the same cylinders are pending, the driver can issue a request for the sector that will pass under the head next. Essentially, we said that everything is under the control of the controller. But you will see from now on that these reading and writing things are actually controlled by both the driver and controller, and sometimes even sharing their responsibility. Okay. If 2 or more requests for the same cylinders are pending, the driver can issue a request for the sector that will pass under the head next. The controller can then select any of its heads almost instantaneously. If the seek time is much faster than the rotational delay. So there are issues, there are cases there. What will happen? If the seek time is much faster than the rotational delay, that means it has already moved to a place, but the sector hasn't arrived there. So that could be another issue, another problem. Okay. So we need to be careful about all these little issues right here. So these are some of the things that you're looking at, some rare cases and what they do. There are quite a few others, but later on we will be talking about how to handle the errors, and we will be dealing with error handling as well. So we will talk about that part very, very soon. The error handling and the backup related issues. When several drives are present in the same controller, the OS should maintain a pending request table for each drive separately. As I said, there is nothing to understand as such, but to remember that how we do it. That's everything comes down to that. How do we serve the pending requests? And when the several drives are present in the same controller, the OS should maintain a pending request table for each drive separately. And whenever any drive is idle, a SIG should be issued to move its arm to the cylinder. So whenever any drive is idle, a SIG should be issued to move its arm to the cylinder where it will be needed next. And that is exactly how this entire thing is carried out or performed. So it's all about arm scheduling, part of arm scheduling algorithm or the mechanism. This is not the algorithm part. These are mechanisms. Okay. Another issue, all the disk scheduling algorithms tacitly assume that the real disk geometry is the same as the virtual geometry. If it is not, then scheduling disk requests makes no sense, because the OS can't really tell where cylinder 40 or cylinder 20 is closer to cylinder 39. And closer to 200 is closer to cylinder 39. That's what I said. It is assumed to be the same. So there needs to be a parity between how your how your cylinder, how your I forget the name. How your controller and how your file system, they individually and independently read the disk space. Okay. So that is what we need to understand. On the other hand, if the disk controller can accept multiple outstanding requests, it can use these scheduling algorithms internally. In that case, the algorithms are still valid, but one level down inside the controller. So it all depends that where you exactly want to implement these algorithms. It could be implemented at the controller level, but it can also be implemented right at the OS level. A few other issues about disk management. Bad sectors. Okay. What are these bad sectors that we are looking at? The bad sectors, as you see, sections don't really read back. So basically, that is one of the problems of the bad sectors, as we can see right there. So we usually call them bad sectors because sectors don't correctly read back the value just written to them. If the defect is very small, the bad sector can be used. Otherwise, the error can't be masked. So 3 of them, controller, OS, and even driver gets involved to some extent to do something about it. What the controller can do, it will remap the bad sector to a spare, that means an extra part, and shift all the sectors up 1. Then the information about the substitution of the bad sector is kept track through the internal table, or by rewriting the preamble to give the remapped sector numbers beside the data must be copied. So what basically it means is information about the substitution of the bad sector is kept track to internal tables. So where you type in the preamble. That's okay. And then when a defect occurs a normal operation, maybe a speck of dust, getting repeated errors in a certain sector, controller can switch to a spare before the sector has actually died completely. So there are quite a few of these options right in there, and that is what we deal with. On the other hand, the OS2 has a role to play in bad sector management. It must first acquire a list of bad sectors, either reading them from the disk or simply testing the entire disk itself. Once it knows, the OS can now build the remapping tables. So whether you do it at the OS level or at the controller level, at any level, these are the same issues. They will take care of these bad sectors in their own way. They will create a substitute. Controller will try to create a substitute, and OS, on the other hand, needs to know exactly where the bad sector is and will try to remap the space to somehow avoid the bad sector. When you do file to file, OS has to hide the bad block file so well that even a backup utility can't find it when you are taking a backup. When you are taking a backup from sector to sector, it's impossible to hide, except that the only hope that the backup program has enough smarts to give up after 10 failed attempts to read from the sector and continue with the next sector. Yeah. The next one that we are going to talk about is sick error. The sick error is basically a mechanical error. That means that it is supposed to move, the read and write head was supposed to move to a particular place, but it didn't simply move there. Why it didn't simply move there? It didn't move there because of some kind of mechanical fatigue or mechanical problem. Okay. So that was one of the reasons that we had. So the next one that we are talking about the seek errors, if you go deep inside and you can see the caused by mechanical problem in the arm. The controller keeps track of the arm position internally. To perform seek, it issues a series of pulses to the arm motor. On pulse, one pulse per cylinder to move the arm to the new cylinder. When the arm gets to its destination, the controller reads the actual cylinder number from the preamble of the next sector. If the arm is in the wrong place, a seek error has occurred. Okay? And so naturally from there will be the seek error. Then the solution is the most hard disk controllers correct seek errors automatically, but most floppy controllers just set an error beat and leave the rest to the driver. Because remember, when we say disk, we are basically going for the seek operation. And when we talk about floppy, we are going for the read operation. So the read operation, read controller just set an error beat and leave the rest to the driver. Because the driver handles this error with particular command to move the arm as far out as it will go and reset the controller's internal data of the current cylinder to 0. If it doesn't, the driver must be repaired. So they are, as we say, that they are kind of coordinating with each other to make things happen, make things possible. That is what they are doing. These are all, as you understand, these are all like a bundle of knowledge that how we do things, okay, and who will take the responsibility. There is no why or there is no logical explanation, logical algorithm behind that. A system has the following properties. When a write is issued to it, the disk either correctly rewrites the data or it does nothing, leaving the existing data intact. Is implemented in software. The goal is to keep the disk consistent at all costs and assume that the errors cannot be detected at the disk written, be detected on the subsequent read. So assume that a correctly written sector can spontaneously go bad and become unreadable. So assume as the CPU can fail or just stop. So if these three scenarios happen, how will we maintain a stable storage? That is the question that we're raising. So what happens in these three cases? And that is what we need to investigate in details. So first, use a pair of identical disks. Okay. and with the corresponding blocks working together to form an error-free block. In the absence of errors, the corresponding blocks on both drives are the same. Either one can be read to get the same result. And there are three operations: the stable write first, then stable read, and a backup. So how do we ensure stable write? To ensure stable write, the first thing we do is to write the block on drive 1, and then reading it back to verify it's been written correctly or not. If not correctly, the write and the reread is done until they start working together. These are the two actions that we take. After consecutive failures, the block is remapped onto a spare and will be marked as usual, and the operation repeated until it succeeds. So basically, keep trying as many times as possible, and to ensure that we don't miss any data or any important information these days. Remember, we discussed LFS, log structured file system, and journaling file system. So JFS, a journaling file system that we discussed in the previous class, will be the one that will be quite effective in this case. Once you have succeeded in writing the data in drive 1, then the subsequent drives can be written. The drive 2 is written and reread until it succeeds. In the absence of CPU crashes, when a stable write completes, the block has correctly been written onto both drives and verified on both of them. So it's not about writing, it's also about verification, because verification is important. To ensure data integrity. Moving on, we have stable reads. Okay. So we had the write, stable write, and we had stable reads, and finally we will have stable backup. So in stable read, we depend on the RAID levels. The one that they are mentioning, the drive 1, is from the RAID level drive 1. The first read block on drive 1 in n times. If all of these give bad ECC, ECC stands for error correction codes, then you start reading from drive 2, because we are supposed to have mirrored them. Given the fact that a successfully stable write leaves 2 good copies of the block behind, and our assumption that the probability of both of them going bad at the same point of time is minimal, so naturally we'll be successful in reading them back. But finally, how do you recover from the crash? After a crash, a recovery program scans both disks, comparing corresponding blocks. If a pair of blocks are both good and the same, nothing needs to be done. That means everything is okay. If one of them has an ECC error or it returns an ECC, error correction code, the bad block is overwritten with a good block. If a pair of blocks are good but different. The blocks from the drive 1 is written onto drive 2, because there needs to be consistency and parity. In the absence of CPU crash, stable storage always works, because stable writes always writes 2 valid copies of every block, and spontaneous errors are assumed never to occur in both the drives. As we said, it is unlikely that both these drives will crash at the same point of time. Just in case it happens, we had the double parity, the RAID level 6, if you can still remember. But that is the most unlikely situation. That's a pictorial depiction of what happens, but it's all in theory. Some optimization and improvement issues. They're comparing all the blocks pairwise after a crash. It's doable but expensive. A huge improvement is to keep track of which block was being written during a stable write, so that only one block has to be checked during recovery. With a non-volatile RAM, the stable write can put the number of block in RAM before starting the write. After completed, the block number in RAM is overwritten with an invalid block. And under these conditions, after a crash, the recovery can check RAM because it's non-volatile. If non-volatile RAM is not available, at the start of a stable write, a fixed disk block or a drive 1 is overwritten with a number of blocks to be stably written. Then read back and verify. If so, the write 2 and verify. Then completed, both blocks are overwritten with an invalid block numbers and verified. And this requires extra disk operation to write a stable block and should be used exceedingly sparingly. But this is not even done, but the second one actually hints at what we call the journaling file system. This much, there is nothing too much into it. And then the next thing is the only thing, real takeaway is the error handling, the stable writes, RAID level, and algorithm. Algorithms are the keys. Okay. Those are the ones that will be more handy, more useful. Wait, I'm in a rush to take your attendance because I just worry that the link will expire. We'll first finish our attendance. Remember again, if you miss it now, I can't do it late. So if you're not there, if you have a mic problem or whatever, you send me a message within the slot time. So the first one, Xuan Huang. Send a message. Ji Kang.
Yes.
Wen Fook. Wen Fook. Yuk Wong. Tuk
Yes.
Quang,
Yes.
Luang Ha,
Yes.
Hu Huang,
Yes.
San Hum,
Yes.
Nafat,
Yes.
Din Min,
Yes.
Wak Hui,
Yes.
Huayan,
Yes.
Kim Tak,
Yes.
Nyat Min,
Yes.
Hien Phuc, Hien Phuc, Wang Hui,
Yes.
Min Quang, Min Quang, Dui Bao,
Yes.
Hui Min, Liam Chuk,
Yes.
and Wak Hum.
Yes.
So a couple of absent. Min Quang, Vin Phuc, you are there. Hien Phu, sorry, Min Quang. Min Quang is absent. Hien Phuc, Hien Phuc, Vin Phuc. Vin Phuc, you had a problem with your lab submission, was it so? Let me check, I can't exactly remember. No. Hum Kang. Sorry. What happened? Yes. So what happened, Vin Phuc? You don't want to give it, but that means that you will not be able to appear in your exam, in a final exam. Because you are still attending the classes, it's up to you. But I'm not going to request you anymore. But remember that in your case, you will not be if you don't submit. And as I can see that you didn't submit. But you didn't submit. So do you want to submit? At this stage, if you want to submit, it's the second week, so you can at best get 50%. So when? Give me a time. When you want to submit. Is it okay that I give you extension to midnight? Okay, all right. I give you an extension. I know that this is a problem. Okay, you get an extension, just so you can see. 11:59 p.m. All right, that's all. And in the next class, we will get started with I/O, input, output. So just point me to the I/O. Okay, if I ask you where to get started, remind me, we will get started with input, output. All right, that's all for today. We'll see you again on Friday. Bye.